Here we are going to discuss example 3.5. Example 3.5 is from unit 3 with regards to discrete probability distributions. Here are some important points with regards to discrete probability distributions. It can simply be put as probability models for numerical discrete values. So point number one is a discrete probability distributions are numerical probability models for random variables. Know the difference between the variable and random variables. The variable has a finite or countable number of values because it's discrete. That's the nature of discrete variables. And a random variable now is a numerical value whose value depends on chance. It's a numerical variable whose value depends on chance, on probability. So the value that it can assume has a probability associated to it. Okay, we'll go into that, more into that later down. Now, the important point here is that the variable is numerical. It can be discrete or continuous. But here in this chapter, we're talking about discrete random variables. So we will only be dealing with discrete random variables. Random variables are denoted using letters such as Y, X, Y, S, etc., uppercase. Now, discrete random variables can have certain distinct values. For example, 1, 2, 3, 4, 5, or 6 in the case of throwing a six-sided dice. So therefore now, when the dice is tossed, you may get a 1. And here the word may, that's a probability annotation. There's a chance that you may get a 2. You might get a 3. There's a probability value that you get a 4, 5, or 6. So that's why they call it a random variable, because of that random nature of chance outcomes that you may get certain values, distinct values for that variable. And the probability histogram is a bar chart in which the horizontal axis corresponds to the value of the random variable, and the vertical axis represents the probability of each value of the random variable. So let's go back to example 3.5. Here we are presented with a discrete random variable x that has the following probability model, probability table, or probability distribution. So this random variable can only assume certain values, 0, 4, or 6, nothing else, nothing more, nothing less. That's it, 0, 4, or 6. And the probability value for each respectively is p sub 0, p sub 1, and p sub 2. Okay, now we must bear in mind that anytime we are looking at a probability distribution, okay, the sum of the probabilities must add up to 1. That's a key component with regards to a discrete or any probability distribution. So now it appears that the expected value, which is the mean, was provided and the variance was provided, 4.1, 4.99 respectively. And we are required to find the values of p sub 0, p sub 1, and p sub 2. Okay, so we have to use this information to find p sub 0, p sub 1, and p sub 2. So we know for sure the formula for expected value is the sum of the products of each value and its corresponding probability. Here it is. Mu is equal to the sum of x times p of x, or the expected value, which is another notation for mu, is the sum of x times p. Okay, so therefore now 0 times p of 0 plus 4 times p of 1 plus 6 times p of 2 must be equal to 4.1. So an equation can be formed. Okay, and the formula for variance now, here it is. You have two formulas. There are two formulas. You've got the second formula, which is a little bit more appropriate for this kind of problem. Is the sum of x squared times p of x minus the mean squared. Okay, so you got to square each x, each variable, each value of the random variable times its associated probability value, and then sum this up, and then find the difference with the mean squared, which of course we are provided with a mean, and that should equal to 4.99. So we can form two equations. And what you will notice that 0 times p of 0 will cancel out. So we are left with 2 equations and 2 unknowns, and we can use simultaneous equations to solve for P and 1 and then P sub 0. Because the third equation now will be the sum must add up to 1. So we have 3 equations there and 3 unknowns, so that's solvable. So here we see the equation was made with the mean. 4.1 is equal to 0 times P of 0 plus 4 of P sub 1 plus 6 times P sub 2. The product, the sum product, and 0 times P sub 0 cancels out. So I left with a first equation, 16.4 is equal to 16P1 plus 24P2. Now another equation was formed with the variance. Okay, and 0 squared times P of 0 plus 4 squared times P of 1 plus 6 squared times P sub 2 minus 4.1 squared. This was simplified, and we are left with another equation, 21.8 is equal to 16P1 plus 36P2. So we can apply simultaneous equation here. Elimination method was used. The first equation was multiplied by 4. It appears that this was to cancel out P sub 1 because 4 4s are 16, and 4 times 4.1, 4 times 6, that's 21.8 for the 6 respectively. But then when we have 16, 16, we can subtract, cancel out P sub 1, and then solve for P sub 2. Okay. And then now, when P sub 2 has been solved, substitute back into any one of the equations to solve for P sub 1, and then use that third formula, the sum of the probabilities must add up to 1. So we add P sub 1, P sub 2, and subtract from 1 to get P sub 0. So simultaneous equation was formed together with the sum of the probabilities must add up to 1. So here we have equation 1 using the mean, equation 2 using the variance, applying elimination method, simultaneous linear equations, and then applying the rule whereby the sum of the probabilities in any distribution must add up to 1. And that will give us our solution for the 3 unknowns, 3 equations, 3 unknowns. So here's some algebra, applied to this question, even though it's statistics, probabilities, but it has some algebraic characteristic associated with it.